So last class we introduced IR spectroscopy, and we talked about how different functional groups give us different signals in our IR. We went through carbon-hydrogen bonds as well as alcohols, right? Alcohols, we got this big broad peak in this region, and that's how we spy our alcohols, okay? So for the sake of time here, I sort of got behind schedule doing too much first semester review. So for the sake of time, I'm going to let you know what functional groups we need to spy, but I'm going to leave it to you to make sure that you know what those look like by watching the posted lecture videos or looking at the slides, okay? It's really not too bad. You can do it on your own. I gave you a few extra attempts on your IR quiz as well so that you can work out the kinks, okay? But these are the functional groups that we need to spy on IR. What we call like your IR active functional groups. Okay, so we talked about those different CH bonds. So we will get a different signal for our alkanes, alkenes, or alkynes. Okay. The one thing that I will say about alkanes is that yes, you can see that carbon-hydrogen peak, that sp3 carbon-hydrogen peak, but all of your samples are going to have that, right? So you kind of know that group of peak is always going to be there. So alkanes look the same as all the other IR inactive functional groups, okay? So if something doesn't have one of those special bonds, you won't see it. So for example, this would be the same as an ether. An ether has carbon-oxygen bonds. Those don't appear in anywhere but the fingerprint region, so you wouldn't see those. All right? Same as an ether or an alkyl halide. Or any functional group without double, triple, or XH bonds. Right, so an alkyl halide, that chlorine-carbon bond, again, that appears in the fingerprint region. So you wouldn't see that. It's going to be blended in with a bunch of other hard-to-read peaks. All right, so then we talked about alcohols. Alcohols give very distinct signals in our IR. Okay. All of our carbonyl containing compounds give a very distinct signal. What do I mean by a carbonyl? Carbon-oxygen double bond, right? We're going to talk a lot about carbonyl compounds this semester. That is the special name we give to that carbon-oxygen double bond. Okay, so first of all, where in our spectrum would we expect this to absorb? The something with H, the triple or the double bond region? Double bond, and it gives this really sharp, pronounced peak in that region. Okay, so again, just a functional group that we can spy pretty easily. Carboxylic acids, they contain both hydroxyl groups and carbonyl groups, so we should be able to spy those. And then lastly, amines. Okay, so these are the sort of patterns that we want to be able to see. Again, if you go through the lecture slides, it sort of points out what you're looking for each. And then at the end, there's even some practice problems where I give you an IR spectrum and I try to get you to match it to one of these here. All right, so look through that lecture video. I'm sure you got it. I want to make sure to spend time today talking about the technique that you're going to use in lab that's far more complicated, which is called nuclear magnetic resonance spectroscopy. Or more simply, NMR. So again, this is just a type of spectroscopy. We're sending photons in, we're seeing what gets absorbed and what comes back out. That's the same as all spectroscopy. But for this one, we're going to be using photons in the radio portion of the electromagnetic spectrum. The radio portion of our spectrum is sort of all the way at this end here. The longest wavelength and the lowest frequency photons. Very low energy photons. Okay? It turns out that at this portion of the spectrum, these photons are interacting with the nuclei of a molecule. Right? Nuclear magnetic resonance, okay? Specifically what they're doing is interacting with the spin state of a nuclei. This is this bizarre property that nobody would have predicted, but it fell out of quantum mechanics and it's later been well established that particles have this property called spin, all right? And we kind of imagine they're doing exactly that, kind of spinning around like tops. You would have discussed the spin of electrons. It turns out that protons and neutrons also have a spin associated with them, okay? And so what happens is these photons, they're going in and they're interacting with that spin state. They're flipping that nuclei from being spin up to spin down, or vice versa, right? So again, these photons are being absorbed. They're being absorbed by the nuclei in these molecules, and they're flipping the spin state. And if that all sounds like bizarre witchcraft, it totally is. Until you go and study more quantum mechanics and become comfortable with it, for right now, you're just going to sort of trust me on that. That's what's going on here, right? How the hell is a photon flipping a spin? Have fun discussing that in a future quantum mechanics course, okay? But for our purposes, that's what's happening here. That's what happens when a radio wave interacts with an atom. Very, very subtle change, very slight change happens. Remember, these are very low energy photons that you're sending in, okay? So, and in order to get like a really good signal, you need a strong magnet. Okay, again, just trust me, this will help you get a sort of better signal. What you'll see when you discuss NMR is that everybody's bragging about their magnet strength, right? You got little tabletops at NMRs that don't give you really good spectra because they have little tiny magnets. And then you have huge ones where you have like a room this size dedicated to an instrument. There's this gigantic looking water tank thing. And really the whole shtick of that thing, why it's such a large instrument, is because there is just a gigantic frickin' magnet sitting in there. All right? You got to be careful when you walk in those rooms. You can't take your cell phone or your credit card, or that NMR will completely destroy any electronic device. Okay? So anyways, that's sort of what's powering an NMR, the sort of mechanics behind it. You got a big magnet in there. So this kind of leads to our, what are the cons of NMR? It is super technically complicated, all right? Very, very complicated theory. We are going to scratch the surface here today introducing this. Truthfully, people who do NMR dedicate their lives to NMR. That's all they do is NMR. We're gonna like barely touch on this theory. You can go down a huge rabbit hole of electromagnetic theory and quantum mechanics. I mean, there is some very cool, very interesting stuff that I know nothing about because that was not my specialty. But I do know that people who do NMR, that's all they do. They kind of fall into this one little rabbit hole, okay? Very, very complicated stuff, both from a technical side as well as a theory side. The other thing is it's incredibly expensive. Right? That instrument that I was just talking about is millions of dollars. We just bought a new one at FCC that's just a little tabletop instrument, $250,000, right? Not even your high-end special room giant magnet one, a one that just sits on a table, $250,000, compared to our $12,000 IR, right? 20 times more expensive for this particular technique. So then why? Why the hell would we care then? Okay, the bottom line is that you get a ton of information, very detailed information about the structure and shape of your molecule. So if you do an experiment and you've made this product, you can stick it in an NMR and you can tell exactly the molecule that you have, right? Down to the orientation of where carbon atoms are, all that jazz, right? Specifically pointing to one molecule. That's the power of NMR. So, kind of a pain in the butt, but if you got the money and the time, or you have somebody that's going to run your sample for you, then you get this beautiful data set that you can analyze and point to your unique molecule, right? Versus IR, which only told you whether or not you had an alcohol group in there, okay? So kind of like I said, the flip side. It's expensive, but you get way detailed information out of it. There's two types of NMR that you're going to use depending on which nuclei you're going to look at, and we're going to do the simpler one of the two first, what's called carbon-13 NMR. Okay, we can just say atoms with even mass numbers are invisible in an NMR. So 99.9% of all the carbon in this Earth is carbon-12, but carbon-12 being an even mass number is invisible in an NMR. What we can see are atoms with odd mass numbers, so carbon-13, one of the rare isotopes. Okay? The nice thing is that everything contains a small amount of those carbon-13 atoms. So that's what we're looking at when we do our carbon-13 NMR. Okay. All right, so for each of our NMRs, how do we go about analyzing? What information do we get? Okay. First, we get what's called the chemical shift. This is simply what frequency photon is absorbed. So if we look at a sample NMR spectra here, we see down at the bottom there's this little lowercase delta in ppm. This is what we call the chemical shift. And just like your x-axis in all spectroscopy, it really corresponds to the frequency or wavelength of the photon that you're sending in, right? So similar to what we saw with IR, right? The x-axis was what photon is being absorbed, what frequency of photon is being absorbed. Same thing here. We're just at a very different portion of the electromagnetic spectrum, so we got different units that we use. Okay? The next thing is the intensity of these peaks. The height of these peaks also gives you information. Okay? In practice, what you do is you get your NMR spectra and then you use a computer and it integrates those peaks. It calculates the area under those curves. So we call this the integration. Okay? This corresponds to the number of carbons. Actually, we're going to use this term, introduce this term, chemically distinct carbons. right? So what do I mean by chemically distinct carbons? Well, if every carbon atom in your molecule absorbed in the exact same place in the electromagnetic spectrum, that wouldn't be very useful, right? Every single molecule would give you a spectrum with just one peak. So it turns out that where a molecule absorbs on the spectrum is super sensitive to what's going on around it. Who's bonded to who? All right, so we're going to practice this idea of being chemically distinct here. All right, by that we just simply mean a unique chemical environment. But like, what the heck does that mean? Okay, so I think it's sort of easiest to see these by analogy here. Okay, let's just take a simple example. We're going to take pentane. All right, we got a 5-carbon chain here. Not all 5 of these carbons are chemically distinct. Some of them have the exact same chemical environment as another carbon in this chain. Okay? In particular, this carbon all the way at this end, it's bound to 4 other carbons down the line. Well, that's the exact same chemical environment as this carbon over here. Right? From a chemical standpoint, they are both bound to a chain of 4 other carbons. There's one other group that has 2 carbons in it. Where's that? This carbon right here. On one side, it's got a methyl group. On the other side, it's got a propyl group. Well, that looks the exact same as this carbon, right? On one side, it's got a methyl group. On one side, it's got a propyl group. So those are 2 identical chemical environments. And then you got this guy in the middle that is in its own unique environment. Okay? So when we're looking for these chemically distinct groups of atoms, really what we're focused on is the symmetry in a molecule. I can tell that this has these 3 chemically distinct groups of carbons because there is a plane of symmetry that cuts right through that molecule. Okay? So in our spectrum of pentane here, we would expect to see 3 peaks, right? Because we got 3 chemically distinct groups of carbons. So 3 peaks in our C13 NMR, because we have 3 groups of chemically distinct carbons. All right, not only that, but remember the integration, the size of those peaks is going to correspond to how many carbons there are in that particular group, right? So my integration value for that red group would be 2, because there are 2 carbons in that group. What would be the integration value for my orange group? Also 2. And what about my green group? How many carbons are there in there? Just 1. All right, so we got these 3 chemically distinct groups. There's 2 carbons in the red group, so we have an integration of 2. 2 carbons in the orange group, so we'd have an integration of 2, but only 1 in that green group, so we'd have an integration of 1, right? So we'd expect 2 big peaks and 1 peak about half the height of the other 2. Okay? Cool. So, different groups, again, where's my slide? There we Different types of bonds will absorb in different places on your electromagnetic spectrum. On that particular example, I would have 3 peaks, but they're all sort of carbon-hydrogen or carbon-carbon single bonds, so they'd all be located down here in this region somewhere. Again, it's so sensitive that they wouldn't overlap. We would indeed still see 3 peaks, but they would be located down here on this end of our spectrum. Okay? If we have higher order, our special bonds, carbon-carbon triple, carbon-nitrogen, carbon-oxygen, they absorb a little bit higher up. Okay? Your double bonded, your sp2 hybridized carbons even further up, and then carbonyls are all the way at the top end of your spectrum here. Okay? So this chemical shift that we said that we can find actually has 2 pieces of information that are really important. Okay? Where on the spectrum is unique to the bond, but almost more important than that is simply the number of peaks, because that tells you the number of chemically distinct carbons, chemically distinct groups. I will say that one big mistake that I made as a student trying to analyze NMR was to focus so hard on where these peaks were in the spectrum, when really you can do a lot by just counting how many individual peaks you have and looking at the integration. In a lot of ways, these are more important, and then I'll go pay attention to where those peaks are, okay? You would be given something like that chart that I just showed as a reference in your lab manual or your lab textbook. All right, my sort of caution is don't get so hung up on that first step. Pay attention to the number of signals you have in your integration first, then figure out where they are on your chart. All right, we'll do an example here in a second that's kind of hammer that home. All right, so let's just look at one where we know what's going on here. And let's convince ourselves that we can see what's what. All right. Here we have this molecule, big ugly benzene derivative here. And here is our NMR spectrum. At the top you have the integration values for each one of those peaks. You can kind of just tell by the height of the peak as well. And then of course we have where on our spectrum we're absorbing here. Okay? So if we look, we have 1, 2, 3, 4, 5, 6 chemically distinct groups. Let's see if we can find that here in our example molecule. Okay? Again, we are looking for a plane of symmetry. Do we have any planes of symmetry in this molecule? Where is it? Right down the middle, right? Cool. So let's put in our plane of symmetry here. That means that these guys are in the same group. These ones are in the same group. Okay, these are in the same group. Am I going to run out of colors? These guys are mirror images. All right, what about these two? Are they in the same group? They are not mirror images of one another. They are sitting on that plane, so they are all by themselves. This would be its own group, and this would be its own group. Okay, so according to our prediction, we have 1, 2, 3, 4, 5, 6. All right, and if we pay attention to our integration, what should be the integration for that red group? 2. What about that orange group? 2. Green and purple are 2. But then these ones are just 1. Okay, so we should have 4 peaks with an integration value of 2 and 2 with an integration value of 1. And that's exactly what we see here. Okay, so again, paying attention first to number of groups and then to my integration. And now I can look on where these fall on my spectrum and try to get a little bit more information. Okay. What's clear is that this one all the way out here, based on my little spectrum here, is going to correspond to those carbonyl carbons, right? Those are the ones that absorb on the far left portion of my spectrum. So I can kind of uniquely say that yes, this corresponds to that red group, integration of 2. Likewise, the one on the other end of my spectrum here is now going to correspond to my alkyl carbons, right? So this would just be my orange group. But now within this cluster here, these all fall in the benzene portion of our spectrum, okay? And so I will leave it to your lab instructor to sort of give you guidance on whether or not you have to uniquely identify these peaks. For my purposes, I would be fine with you saying this is either purple or green or purple. Likewise with this one. How do I know that they have to either be green or purple? Because there's 2 of them, because of the integration value, right? Whereas the other ones, I can't really tell which one's which, but I know it's either the lime or the highlighter yellow. All right, I can't really uniquely assign peaks in that one. They're really close together. Okay, cool. So let's just do an example. This one we sort of knew the punchline here. Let's do another one. Okay, we are going to synthesize a molecule called xylene, which is a fancy way of saying dimethylbenzene. We will talk a lot about benzene compounds this semester. That is a type of functional group. Those aromatics are not what you covered in the first semester. We're kind of heavy on that in the second semester. So if I had my benzene, to be clear, benzene is when you have that famous hexagon, but you got these alternating double bonds going on. Okay, so dimethylbenzene means that there's 2 methyl groups, but depending on my orientation of these methyl groups, I could actually get different stereoisomers. So I could either put them directly next to each other, or I could space them out so that there's 1 carbon in between. Or they could be located on opposite sides of that ring. And again, you wouldn't know this because we haven't covered this, but we have special names for these orientations. This would be the ortho, this would be the meta, and this would be the para of each of those, of xylene. Okay, so we did this reaction, we synthesized our xylene, but we don't know which one of these constitutional isomers, my bad, which one of these constitutional isomers we have, all right? And so that's what you're gonna do. You're gonna take a minute and you're going to look at our NMR spectrum here, and you're gonna tell me which one of these xylenes did we synthesize, okay? You will see that there's not much useful information looking at where that absorbs on the spectrum. You would expect the same sort of regions of absorption for all 3 of these molecules. But if you focus on the number of chemically distinct groups and the integration of those groups, you can narrow down which one it is. Okay, so looking at your 3 possibilities, figure out how many chemically distinct groups you would expect and how many carbons you would expect to be in each of those groups. for the sake of time, I'm going to start going through this here. For my orthoxylene, do I have any planes of symmetry? Yeah, right down the middle here. So that means that these carbons are going to sit in the same group. These carbons are going to sit in the same group. These would be in the same group. And these would be in the same group. So then how many signals would I expect to see if I had the orthoxylene? I get one signal for each one of these chemically distinct groups. So I have 1, 2, 3, 4. I would expect 4 peaks on my graph, right? Each chemically distinct group gives me a different signal. What would be the integration of the blue group? 2. What would be the integration of the red group? 2. And the orange group? And the green group? Cool. Do I have a spectrum with 4 peaks, each that have an integration of 2? No. Okay, well then this can't be our ortho. What about metaxylene? Do I have any planes of symmetry? Okay. How many chemically distinct groups of carbons do I have? So these ones are mirror images. These ones are mirror images. These ones are mirror images. But these two sit on that plane, so they don't have any partner on the flip side, right? So this would be by itself, and this is by itself. Whoops. So I would expect to have 1, 2, 3, 4, 5 chemically distinct groups. And let's look at our integration. What would be the integration of that red group? 2. What about the orange group? And the green group? And what about this purple group? Just 1. And my blue group? 1. So does that match our spectrum that we have here? 5 distinct peaks. 3 of them should give me an integration of 2, and 2 should give me an integration of just 1. So check, check. We indeed have our metaxylene here. Okay. Just to be clear, the pair one is probably the most difficult in order to find number of chemically distinct groups. Do I have any planes of symmetry? Yeah, I don't have just one though. I actually have 2 planes of symmetry, right? I can cut this thing this way, fold it in half. I can also do the same thing this way. So because of that, these 2 carbons will live in the same group because they're symmetric about this middle one. These 2 carbons will live in the same group, but all 4 of these are going to sit in that same group of chemically distinct carbons. If you cut out this little image and you folded it up on each of those planes, you would see that all of these green carbons overlap. Okay? Look, counting chemically distinct groups, being able to spy chemically distinct groups is not the easiest thing in the world. That's absolutely going to be the first thing that you practice in your homework because it is kind of difficult. Again, you're looking for your planes of symmetry. That's how you're finding these groups of carbons. All right, so now we're going to introduce, we talked about C13 NMR. The other one is what's called H1 NMR. Exact same principle, but now we're looking at groups of chemically distinct hydrogens. And so for H1 NMR, you get the same pieces of information that you do from carbon-13 NMR. All right, you have your chemical shift, where it absorbs on the spectrum. Okay, again, from that, the 2 things that you note is where it absorbs, but even more importantly, how many peaks you have. you will also get integration values. And again, these will tell you the number of, in this case, hydrogens in your chemically distinct group. All right, so all the skills that we just practiced for carbon-13 NMR, they are all directly applicable to H1 NMR as well. Hydrogen NMR, though, gives you one additional piece of information, and that's what makes it so freaking powerful, something called the multiplicity. And the multiplicity tells you the number of hydrogens that are on your neighboring carbon. All right, so, well, we'll worry about this multiplicity business here in a second. Let's take a very simple example. We're going to take propane here. I want everybody to take a second and tell me how many chemically distinct groups of carbons we have here. Really groups of hydrogens, I guess, but same concept, right? They all live on a carbon. How many do we see? Two. Cool. Let's just. We have these. Whoops. And then we have this one in the middle here. Okay. How many hydrogens live in that blue group? 6, right? I got 3 on each of those methyl carbons. So my integration value would be 6. And what about in that red group? 2. Okay. Usually your integration value, I don't know about your particular instrumentation or what your instructor is going to give you. Typically you get for your integration values, they're fully reduced. So really you would get an integration of 1 to 3. All right. That's typically what the instrument spits out. But you know, one group has 3 times as many carbons as the other. This particular data set that I use actually tells you number of carbons here, or number of hydrogens. So, first of all, right off the bat, let's just convince ourselves that we see, in this case, they're cluster of peaks, but we see 2 distinct clusters of peaks. One corresponding to our blue group has that integration value of 6. The other one corresponds to our red group, has that integration value of 2, right? So again, just like before, number of signals, all right, as well as our integration value. But now our peaks aren't just one peak, they're split up. And this is our multiplicity that we were talking about. What we're going to do is for your multiplicity, you're going to count the number of peaks that you have in your spectrum. Okay, so in this case, this cluster of peaks has a multiplicity of 1, 2, 3, 4, 5, 6, 7. What about this cluster here? What's my multiplicity? 3, 1, 2, 3. Okay, and again, your multiplicity tells you about the number of hydrogens on the neighboring carbon. So how does that work? All right. You have your multiplicity. -1 equals number of neighboring hydrogens. So given our known spectrum here, right, we counted our multiplicity, but we know that this molecule corresponds to propane. Let's just make sure this all checks out here. All right. We again said that this cluster with its integration value of 6, this corresponds to my blue group here, my blue group of hydrogens. Okay? And we said that this group has a multiplicity of 3. So then how many neighboring hydrogens must this group have? 2, right? Multiplicity minus 1. And if we look, are those blue hydrogens neighbors to 2 other hydrogens? Yes. So the reason why that peak is split up like that is because you're neighboring, let me just get rid of this so it doesn't get too busy, those 2 hydrogens in the red group. Okay? Those red group hydrogens, how many neighbors do they have? 6. We got 3 on one side, 3 on the other. So what would we expect the multiplicity of that peak to be? 7, one more, right? And indeed, when we looked at our spectrum here, that blue group was split up into these 7 peaks here. Okay? So hydrogen NMR, a little bit more of a pain in the butt, but there's a lot of information in there. Generally speaking, at least for me personally, I will use hydrogen NMR if I can, unless we're talking about a compound that doesn't have a lot of hydrogens, like for example, those aromatic compounds that we were looking at earlier. There's just really not a lot of hydrogen, so there's not a lot of information there. So typically you would use H1 NMR for simpler compounds with a lot of single bonds, and you would use your carbon-13 NMR for your aromatic compounds, just because there's not a lot of hydrogens. All right, we're not really going to have time to do this example justice here, so I'll give you the punchline, okay? Typically, you don't go into the lab with a spectrum and no other information, right? You have an idea of what you expect, okay? And what we do is we usually pair these techniques with IR, so we know what functional group is there, but also mass spec, which tells you your chemical formula, okay? So for example, this compound here has a chemical formula of C4H9Cl. And there are several different molecules that you could draw with that same chemical formula. All right, but the only one that would correspond to this NMR spectrum right here would be the 2-chlorobutane. All right, and you can sort of convince yourself that this group here, first of all, this would have all 4 chemically distinct carbons. There is no plane of symmetry. Okay, and you can even say that this red group must correspond to this one here. There's a multiplicity of 2. So how many neighbors does that red group have? Just 1. And where does that 1 live? In our orange group here. Okay, and so you could kind of go down the line. This must correspond to our orange carbon. This must correspond to the green carbon. And this must correspond to the blue. And both the multiplicity information and the integration information point you in that direction. Okay, cool. So when you do your assignment, it'll again start kind of with the basics, counting chemically distinct groups, and then sort of putting it into practice, counting multiplicity and number of neighbors. Okay, cool. This is a technique that you will use in lab. I have to teach it to you, sort of tee it up so that you can actually use it. We're not going to be really doing much spectral analysis in the lecture portion of the class. Next week, we'll give you a much better sort of picture as to what the course looks like, where we start back in on our lecture information, picking up with conjugated dienes. Cool. Enjoy your weekend. Long weekend. Nice.